Somehow we got back. This is crazy. All right. Well, make sure. Okay. Can you hear me okay? We'll give this one more shot. I'm running off my phone right now. Okay. All right. Well, let me call back where we were. All right. So we did talk about the structure, how we came up with it, and this is how we came up with it. And we had the general formula of AB2E2, which then we utilized the shape table to give us specifically the geometry and the name of the shape. So looking for AB2E2, that's the last one down at the bottom. And that is the structure of water, where we have the two hydrogens bonded to the central atom of oxygen. And then we had two lone pairs on the central atom. Now that shape that you see, that's just going to represent like an orbital that's out there where those two electrons exist. I also stated that when you end up with lone pairs on the central atom, you can almost unequivocally say, hey, I'm going to have a polar molecule, okay, regardless of what else is bonded to that. But more on that later on. I'm just kind of give you a tidbit of information here, okay? So with that general formula, we can determine the geometry and what it looks like three-dimensionally, and the name of that shape, and then that bond angle, which represents the angle between whatever's bonded to the central atom, are pretty, I would say the majority of the molecules exist in what is called a tetrahedral shape, and that is that one there at the AB4 geometry, which is listed, wrong one, which is listed right here. Okay. And if we think about this for a second, you see that line there, which that arrow represents two electrons, and there's four pair around the central atom, and they're negative, and they want to distribute themselves far away from each other because they repel. So after everything's done, that is what they end up with, this particular shape, tetrahedral. Now, if we were to remove one of these moieties, let's say remove whatever this is, and just put lone pairs, well, because those lone pairs are two negative electrons and no longer being shared, they have something that looks like this, they tend to repel each other. And what results in is that bond angle that started off at 109 now gets crunched like an umbrella that's been opened up, by the strong wind, inside out. The bond gets crunched a little bit, and you get in something that looks like this. Okay, if one of those species, one of those whatever was bonded to the central atom, one was removed, and just the lone pairs are left off. And anyway, here we start getting lone pairs in the central atom, and now we start changing the characteristics of that molecule and make it into a polar species. Most of the time, depending on the structure, a tetrahedral configuration generally, and I emphasize the word generally, ends up as a nonpolar moiety. The moment we start removing whatever's bonded to the central atom and introducing the lone pairs, then we start getting into polar molecules, okay? And so changing the total property of this compound. All right, so let's go back to this one. So that's how we came up. Notice here, if you count the electrons, we have a total of 8 valence electrons that we had to work with. And we still have it around the molecule. So you got to keep inventory, making sure if I calculate 32, I'm going to end up with 32 electrons. or 4 or 8, whatever the case may be, valence electrons. Let's do a couple more examples. All right, so we have this species, and I realize right now you don't know what they are. That's okay. All right, but we know just by the symbols what atoms we're working with. The first one, HCN. We got hydrogen, carbon, and nitrogen. Okay, we've underlined the central atom for you. Okay, so carbon is the central atom, which tells you that the hydrogen and the nitrogen are bonded to carbon. Okay, how they bond, whether what type of bond, being single, double, triple bond, depends on the valence electrons that we have to work with. All right, so first thing we do, grocery list. I call that a grocery list of your valence electrons. Okay, we need to figure out exactly how many we got to work with. And so we got 1 hydrogen, okay, 1 carbon, and 1 nitrogen, right? Now, how many valence electrons does hydrogen bring? 1, right? Carbon, because it's in group 1A. Carbon is in group 4A. Okay, so we got 4 valence electrons. Nitrogen is in group 5A. Okay, so we got 5 valence electrons coming from nitrogen, and we only got 1 of each atom. Okay, so that gives us a total of 10 valence electrons. So that is what we got to work with, or by pair, right? Because 10 divided by 2 is 5. Pair, because every bond represents 2 electrons or a pair. All right, so we got 5 pair to work with, so we got to keep track of that. Since we're given that carbon is the central atom, we can very quickly write carbon, okay? And nitrogen and hydrogen are bonded to them, so we can draw 1 line to the nitrogen and 1 line to the hydrogen. Guess what? That takes care, we had 5 pair to work with, okay? That took care of 2 pair. That means we got 3 pair left of the original 5 pair, okay? Or 10 valence electrons. Now, the question is, where do we put them? Okay, well, we can't put them on hydrogen. Remember that. Why? Because hydrogen already is full. It's a duet. There's 2 around being shared with carbon around hydrogen. So that's good. And so the only place to put them would be on the other atoms, carbon and nitrogen. Now, where you put them makes no difference. I just, by personal preference, I tend to start on the outside atoms and put them on them and work my way in, okay? Whether you do that, that's fine. What you don't, it doesn't make a difference, because eventually you got to start counting the octet, and then you start making double bonds and triple bonds as needed. So I'm just going to put those 3 left over around the nitrogen. So I got 1, 2, and 3. So that took care of the last 3. I got 0 pair left. Perfect. Check your inventory. I got 1, 2, 3, 4, 5 pair. Okay. 5 pair. I'm going to mark them again. 1, 2, 3, 4, and 5. And let me, I put them in yellow so you can see them. That, don't get confused. Okay. Now we check the octet. We know hydrogen's happy. We're good with that. We take a look at carbon. Around carbon, there's only 2 pair around carbon at this point. Okay, so carbon's not stable. It's only 2 total, 2 pair of 4 electrons. See, the one on the left shared with hydrogen, and the one on the right shared with the nitrogen. So we got to make note of that. Nitrogen, count them around the nitrogen. Guess what? We got a total of 8 electrons or 4 pair around nitrogen. Nitrogen's happy, okay, but carbon is not. Now, we can't just add more valence electrons. Here, we have to share and create double bond. So what we do is we take one of these pair and make a double bond. And so we result in this hydrogen bonded to carbon, double bond and nitrogen. I still got 2 lines left, okay? Go back and do an inventory. I can't overemphasize that because this is where you can lose pairs and then you got a mess. So go back, still got 10 valence electrons with 5 pairs. I got 1, 2, 3, 4, 5. So I'm still good to go. Check on the octet. Nitrogen's still happy. We didn't do anything. We just made a double bond, but it still has 8 around it. Carbon, on the other hand, went from a total of 2 pair to 3 pair. That's only 6 valence electrons. Still not happy, right? So what do? We create another bond. We share. I shouldn't say create. We take electrons from one atom and put them in to make another bond, okay? So we take from Peter and share with Paul, so to speak, if you will. So we're going to take it, which one you do, it makes no difference. And I'm going to take this one and just make another bond there. And so now I go hydrogen, single bonded carbon. Now I created a triple bond. And now I have my structure. Well, inventory, don't forget that, check. I still have around here, I still have a total of 5 pair. Remember, that's what I worked with. That's what I come up with. I got to use my 5 pair. So I got total 5 lines there. 1, 2, 3, 4, 5. So I'm still good. I didn't lose any in making these pairs. Now check the octet or / duet. Hydrogen as always is still good. Carbon now has 8 electrons around it. 3 pair are being shared with the nitrogen and 1 pair is being shared with the hydrogen. We look at nitrogen, it also has 8. One of them is a lone pair, it's not bonded, okay? And the other 3 pair is shared with a carbon. So there's a total of 8 electrons around nitrogen. So nitrogen's octet has been fulfilled, carbon's octet has been fulfilled, and hydrogen's duet has been fulfilled. And so we end up with that formula, HCN. Our general formula, let me draw that. Let me draw that differently, different color. Let me try blue. Our general formula here would be A, B, and 2. That's a general formula. A is a central atom, which is carbon, and B2 are the atoms bonded to the central atom, which is the nitrogen and the hydrogen. There's no E here. There's no lone pair on the central atom. Yes, I know there's a lone pair on nitrogen, but nitrogen is not the central atom. We only care about the lone pair on the central atom. Now, with that bit of information, next thing you do is you go to the shapes table and look for AB2. And that is the very first entry right there, AB2. And so this could be carbon in here, and there's hydrogen, and this could be nitrogen. And that geometry is called linear, okay? And that bond angle is 180 degrees. All right. Now, the question is hydrogen cyanide, cyanic acid, HCN, is it polar? Well, we'll come back to it, okay? We'll come back to the polarity of the molecule because we need to grasp the concept of a polar bond before we can understand further the polarity, overall polarity of that molecule. Okay. All right, so let's clear this up. We go back and nope. And that's what we came up with, the same thing the PowerPoint has. All right, now let's take one with a little bit more valence electrons to work with, okay? All right, CHF3. this is a generic name. It's a fluorohydrocarbon. Okay, but that's not important right now. What we do know, based on what we see here, we have carbon in the central, because it's underlined. Bonded to it is hydrogen, and guess what? 3 fluorides. Okay. All right. Well, first things first, we need a grocery list of valence electrons. And so we have 1 hydrogen, which, valence electrons brings one valence electron to the table. And then we got 1 carbon. Now I need to know I'm saying 1 carbon because if you have 2 carbons, then obviously you're going to multiply your valence electrons by 2 or 3 or 4, whatever number of atoms you have. So carbon brings in 4 valence electrons, right? Now, how do I know that? Periodic table, I find carbon's in group 4, IVA, 4A. Okay. Now we have 3 fluorides. Okay. Now, what group is fluoride, or fluorine, if you will? Right now it's a fluoride because it's bonded. What group is fluoride? Okay, what do we got? It's in group 7. That's correct. So therefore, I have 7 valence electrons, but I have 3 of them, right? So 7 times 3 is 21. So I got 21 valence electrons coming from the fluorides. So I have 1 plus 4 plus 21 isn't that 26 valence electrons? Check my math. Keep me honest here. I have 26 valence electrons. All right. And I take that and I divide it by 2 because I like to work with pairs. So I got 13 pairs to work with. Okay? 13 pairs. Now, carbon has been highlighted as the central atom. So I can very quickly, well, not as quick as I thought, fairly quickly, put carbon in the central atom. I know there's a hydrogen bonded, and I got 3 fluorides bonded. So I can very quickly throw those in. Okay, the 3 fluorides in a single bond and 1 hydrogen single bond. That takes care of 4 bonds, does it not? Right, so I got to keep track of that. So I got 19 pair to work with. Okay, now you have to ask yourself, I got 9 pair to work with. Did I say 19? That was my bad. 9 pair. Okay, from the original 13. So I got to put them someplace. Well, again, check the octet around and the duet around the atoms. Hydrogen, always, I got 1 bond, you're done. You can't add any more to hydrogen, okay? Because the maximum is 2 for hydrogen. Look at carbon. There are 4 bonds around carbon. Each bond has 2 electrons. Therefore, I can't add any more electrons to the carbon. What if you do this? If you say, all right, what if I put it like this? What's wrong with that picture I just drew? I put in 2 dots. I just make it 1 line. What's wrong with the picture of putting 1 line in that carbon? Too many electrons. Now I have 10 electrons around carbon. It has 8 already. By adding 2 more, you have violated the octet rule, which means that you can't put any more on carbon. So where must they go? They must go on the fluorides, okay, 9 of them. And you can just simply start, okay, remember, because right now the fluorides only have 2 around it, and we got to have octet. So I can just go, put them in there. 1, 2, 3, 4, 5, 6, 7, 8, and 9. That took care of my 9. I got 0 pair left over, right? Double check your lines, your bonds, okay? Make sure you got 13 pairs sitting there. And sure enough, there's 13. There's 9 around the fluorides, and then you got the 4 inside with the carbon, and you're good to go. 9. All right. So now, once you've done that with checking your pair of electrons, go and check the octet. Make sure everybody is happy. Hydrogen's okay. We just talked about carbon. Carbon's good with the 8. Got 4 bonds. And every fluoride there has 8 electrons around it, 4 pair. 1 pair is bonded to the carbon. The other 3 are lone pair, okay? They're not bonded. They're just sitting there on the fluorides. And so everybody is happy, if you will, okay? Now, general formula. A, always have A, okay? B is how many atoms are bonded around the central atom. And there are 4. Exactly. There are 4. 3 of them happen to be fluorides, and 1 of them is hydrogen. Okay. So our general formula is AB4. Now let's go find out and determine the geometry. We go to the shapes table and we look for AB4. And as we spoke about earlier, that is the general, most common structure that we see out here. And so this could be carbon sitting here right there. This could be hydrogen, and that's fluoride and fluoride and fluoride. Okay. It has a tetrahedral configuration or name of the shape. There is 3-dimensionally is that picture, and its bond angle is 109.5. Okay. We'll learn about polarity here in a bit, so bear with me. All right, so we have that structure. Now here comes another one that's very interesting, okay, because it introduces some stuff. Carbon dioxide, okay, carbon dioxide. All right, so what do? Grocery list. We have 1 carbon, which gives us 4 valence electrons, and we have 2 oxygens, right? 2 oxygens. Each oxygen brings in how many? How many valence electrons does oxygen bring? 6. Exactly. It's in group 6. There are 2 of them, so therefore we have a total of 12. So we got a total of 16 valence electrons, or 8 pair. Okay, we got 8 paired to work with. All right, so carbon's the central atom, and so we can very quickly write carbon and then bond to it an oxygen on each side. Okay, that takes care of 2 pair. So we got 4 pair to work with left over. Oh. Okay. Now, where do we put it? Well, we can put them anywhere you need to. I tend to want to put them outside, if you will. I mean, 1, 2, 3, and 4. Wait, there's something missing here. Did I make a typo? Anybody pick up on that? Okay. How'd you come up with 6 pair? Okay. The carbon has 4, right? Oxygen's in group 6. There's 2 oxygens for carbon dioxide, so it's a total of 12, right? And plus the 4, isn't that a total of 16? Okay, which gives you a total of 8 pair. Okay. And what did I do? Where did I go wrong? Oh, very good. That's me. Yeah, keep me honest, guys. See, I subtracted, instead of subtracting 2, right? I subtracted 4. And so when I looked at the number, I'm like, no, that's not right because I won't have enough in there. So that's why keeping inventory is important. So that means I got 6 pairs left to work with. Okay. So don't make the mistake I just did. All right. So I got 6 pairs. Now, what would have flagged that is if I would have put 4 pair in there, I would have been like real short. I couldn't borrow too much. All right. So now I got 6 pair. Where you put them makes no difference. Like I stated before, I just go on the outside, fill them up, and work my way in. And so I'm going to do that. I'm going to go 1, 2, 3. That oxygen's happy now. And I'm going to fill the other oxygen, 3, 4, 5, and 6. All right. And so go back and check, double check. That took care of the 6. I got 0 pair to work with now. Check my math, make sure I'm doing okay. Check my bonds. Okay, I should have 8 pair there, total of 8 pair. And everything looks like it should. I now check your octet. The oxygens are happy. There's 8 electrons around it, but the carbon is not. There's only a total of 4, the way I wrote it, around it. So what I do is, like I did with the first example, I borrow from Peter to share with Paul, so to speak. So I'm going to just take one of these guys here and make a double bond, and just take one of these guys here and make a double bond here. And I'm running out of space, so I'm going to go up on top. And so when I end up with that, I end up with carbon, double bonded oxygen. Here's my 2 pair, double bonded. Okay. Now go back and check my lines, make sure that I am still at 8 pair, and I still have 8 pair there. Altogether, 4, 5, 6, 7, 8. And so, okay, I need a double bond because remember, I need to have octet around all of the atoms. See, before that double bond, let me change the color here. Before that double bond, I only had 2 there and 2 there for carbon. I had a total of 4 electrons for carbon. Okay. Around the oxygen, there's a total of 8 electrons. Okay. And the same is true for the other oxygen. 8 electrons around each oxygen. So the oxygens were good, but the carbon only had 4 electrons. So we need to get 8. We need to make a double bond. We cannot just create electrons, okay? Because we only have 8 total to work with. That's it. And so whenever one of the atoms is short an octet, then what we do is we start creating double bonds, and if that's not enough, we create a triple bond. The maximum you can go would be a triple bond. Okay. Does that answer your question, Victoria? Okay. And so that results in this structure up here. Okay. Where we took those electrons that were right there, and I just drew an arrow to show I'm going to make a double bond, and I created a double bond. So now I look at oxygens. Both the oxygens are happy now. We're happy even to begin with. They had 8 around it. Okay. But now the carbons have a total of 8 around it too. There's 2, 4, 6, and 8 around the carbon that are being shared with 4 of them are shared with the oxygen on the right, and 4 of them are shared with the oxygen on the left. So there's a total of 8 around the carbon. And so the octet has been fulfilled. So that is the general formula structure for carbon dioxide. Now we go to the general formula, I should say. That is the structure for carbon dioxide, but the general formula would be AB2. Okay. And AB2, very similar to the one we just previously did. And we got a linear molecule. There's AB2 with carbon in the center and then the two oxygens there. And with bond angle 180 degrees. Now, because of the structure, the way it was put together, we're going to learn that carbon dioxide, even though it has what we call polar bonds, is actually nonpolar. But more on that in a bit. All right, so that is the structure we come up with for carbon dioxide. Okay. All right, now we got one more, and that is NH3, which, by the way, is the structure, the formula for ammonia. I'm sure you used ammonia someplace. Window cleaners are used it. Floor cleaners have ammonia. Old baby diapers have ammonia. All right, so let's do our inventory. So we got nitrogen. How many valence electrons does nitrogen bring? Oh, that's not good. Exactly 5. Why? And so there's one nitrogen that brings us 5 valence electrons. There are 3 hydrogens. Each one brings 1, correct? And so we have a total of 8 valence electrons or 4 pair, okay? Nitrogen is a central atom, so we can very quickly draw nitrogen in the middle and then draw the 3 hydrogens bonded to the hydrogen. We can draw the hydrogens bonded to the nitrogens. That takes care of 3 of the pair. So we got 1 pair to work with left over. As stated before, as the case here, okay, and in here, we cannot put any more on the hydrogen. All 3 hydrogens are happy. They got their duet field. So the only place I can put it, what's left over, is right there. Now I'm going to just do the 2 dots. You can make the line, 1 line, that's sufficient. Okay, so now we're done. We still got 4 pair, okay? And we can check the octet / duet. Hydrogen's happy. Nitrogen, also happy. There's 80 electrons total around nitrogen now. And so its octet's fulfilled. And now we need the general formula. We got A, which always the case. We got B3 because there are 3 hydrogens bonded to the central atom. And guess what? We got 1 lone pair. We got 1 lone pair on the central atom. So our general formula is AB3E. Sends us to the shapes table. And we look for AB3, and there it is right there, AB3E. Okay, its particular name is trigonopyramid. And that bond angle is now decreased quite a bit, not quite a bit, but has decreased from the standard or the reference 109. Simply because we have a lone pair on the central atom, they take up a lot of space and they push whatever's bonded to the central atom in, okay, and making that angle much less than 109.5, okay? Now, FYI, remember what I said about lone pair in the central atom? What can you say about it if you need to know that information down the road with respect to polarity? Is it a polar molecule? Yes, simply because the lone pair is in the central atom, and we'll learn more about that as we progress here pretty soon. Okay. And so there is the formula. And so using, to rehash, taking the valence electrons that we have to work with, which means you got a formula, you're given the central atom. Yes.
Could you repeat again for the angles that you compare the 2 angles, one that was a polar molecule which has 2 long pairs, and the other one that's the AB4 and the AB3E?
Uh-huh.
Could you repeat again, please?
Yeah, the bond, let me draw this here. The bond angle, let me see, we'll draw red. One moment, guys. Okay, sorry. When we talk about the bond angle, what the molecular structure here, it's an attempt to draw a three-dimensional model the way it's drawn, given the two-dimensional world picture that we have here. And so if you can, maybe if I draw it different way. Okay, let's take that. Let's take carbon. Now, if I draw this in this manner, this wedge that's shown here, that represents, if I were to try to draw this in a three-dimensional perspective, and we got a two-dimensional image here, these two hydrogens that I just drew are on the surface of the monitor. Okay. Now, this wedge that's coming out of the monitor, that's what's representing a hydrogen atom coming out of the monitor. Okay, and then this hash mark represents a hydrogen that's going toward the back of the monitor to give us this three-dimensional perspective. Okay, so between here and here, there is an angle between here and here, these two hydrogens. And that particular angle is 109.5 degrees. Okay, that has been determined using what we call spectroscopic methods, alternative methods. Okay, it's 109.5 degrees all the way around. Now, let's take this example down here. When these lone pairs show up in a central atom, we're going to put if this was the case, and I want to use nitrogen better, it's a lot more specific example. We would anticipate that these lone pairs would be like configuration like the tetrahedral. But the problem, not the problem, is that these electrons, two electrons, repel each other. They're free, they're not bonded, so they repel each other, which causes, it's like an umbrella that's been blown out of, to strong wind. It's kind of shoved the angle out. This angle now that we would have thought to be 109 now has been pushed in and is much less than 109 because these lone pairs take up more space. Okay, and remember that these are electrons. This bond here is electrons, and they're negative too, but they're bonded. So those lone pairs are going to be pushing against the bonded electrons, making it move away because they repel each other. So that causes this bond to be less than 109.5. Okay, does that kind of explain it a little bit?
Yes, thank you.
Sure. All right, so let's go back. All right, so to summarize all this, is this that we given a formula, we determined the number of valence electrons that every atom brings to the structure of the formula, okay? And we determine that from its position on the periodic table. Its group number tells us how many valence electrons. Because remember, those valence electrons, that's where all the actions happen. That's what making the bonds. All right. So based on the total number of valence electrons, and we divided that total number by 2 to give us a pair, which I like to do to work with pairs rather than having to do with individual electrons, because I can simply very quickly draw lines, okay? You're given the central atom, and then anything else around that's shown and given to you is bonded around the central atom, just like NH3. Nitrogen is the central atom, and those 3 hydrogens are bonded around the central atom. Once we know that, we start drawing bonds to whatever moiety, whatever atoms are bonded to the central atom. We can start taking care of subtracting the number of bonded pair that we have. Then whatever's left with respect to electrons or pairs of electrons, we put on the atoms to fulfill the octet. Normally, like ammonia, like we just did, very quickly, the only place we can put the last pair is on the central atom. Well, once we put all the pairs of valence electrons, if anybody is shorthanded because the octet has not been fulfilled, we start borrowing from one atom to create double bonds. And if that doesn't work, we create triple bonds. You won't find anything greater than triple bonds, either single, double, or triple. And we create these bonds with the valence electrons that I have. I got to emphasize that. Create doesn't mean I just arbitrarily just pick up some electrons and put them in there, because I have an X number of valence electrons I got to work with, and that's it, no more, no less. And then I create the double bonds and triple bonds such that everybody now, the octet / duet has been fulfilled, okay? Remember, that's the magical 8 number. You want 8 electrons around itself, unless it's hydrogen. And then hydrogen only needs 2, okay? So HCN, what we did is we added up the valence electrons from every atom, okay? That's 5 from nitrogen, 4 from carbon, 1 from hydrogen. Gives us a total of 10 valence electrons, which we have 5 pair. And we place the central atom bonded to the hydrogen and the nitrogen. Told us how many pair we got left. Okay, we just simply put those electrons around what's left. Okay, 5 pair, check the octet, and then we created double or triple bonds if needed, so that everybody's octet has been fulfilled. Remember, those electrons that are bonded are shared between 2 atoms, so they count to each respective atom that you have. So that carbon has a triple bond that is shared with the nitrogen. So 6, the number 6 goes to that carbon, but then it has a single bond that it shares with the hydrogen. So those are 2 more electrons there. So now carbon has 8, then all 8 of them are being shared. Okay, nitrogen in this picture has 6 of them that are shared with the carbon, but only 1 that is lone paired that's not being shared. Okay. All right, now they kind of introduced this a little bit early, which is kind of shouldn't have, but I need to introduce you to the other periodic table, and let me put that up. Okay. Now, from the periodic table, on the bottom left corner, there is what are called polyatomic ions. Now, we've introduced you to ions. Ions are nothing more than elements that have lost or gained electrons that end up with a charge either positive or negative. Okay? Now, there are some ions that have a positive and negative charge, but they come in a packet. They are called polyatomic ions. And that's polyatomic because there's more than one atom involved in this polyatomic ion. And they come together as units, okay? They're not separated. And they're shown on the bottom left table of the periodic table. Okay. Bottom left corner. Now, you can see they each have a charge. Now, we're going to get to know these quite a bit later on the road. But the thing to keep in mind here is they all have a charge. There's only one that's a cation, that's the ammonium. That is a nitrogen bonded with 4 hydrogens that has an overall positive charge. That positive charge is for the whole unit. Now, the thing about these little packets, you keep them, if you need to use more than one, we don't separate them. They come together as a packet. Remember that. So the one NH4 plus, it stays together NH4 plus. If you look on the far right, you see NO3 with a minus. Oh, cutting off again, huh? Oh my goodness gracious. It's my phone now. In and out. Okay, how about now? I can't blame this one on Cox. This is my phone. I blame this one on Walmart Family Mobile because I'm running off a hotspot. Okay. All right. So these are polyatomic ions on the periodic table. Be familiar with them. We're going to use them quite a bit. Okay. Thing to remember, they come together as a unit and they are ions and they have a charge. Okay. Most of them are negative, but you only got one that's a positive. So we're going to talk about how to come up with Lewis dot structures for these polyatomic ions. The process is the same as far as the initial steps. And that is we add up the valence electrons and then come up with a number. And then we add or subtract a charge. Depending on the charge, if it's a positive, we're either going to add whatever charge number it is or subtract whatever charge number it is. Okay, that's the only difference. And then the final thing is when we write the formula, we put a bracket around it because it is a charged species. It's an ion. Let's do an example. Well, first of all, if the polyatomic ion is negative charge, you can see from that table, the majority of them are negative. We only got one positive one. What we do, we have to add an electron or add electrons based on the charge it has. So it has a negative 1, we add 1. There's a negative 2, we add 2. Negative 3, we add 3, etc. Okay. If it's positive, then we have to take one number away. Again, by the magnitude of the charge. So it's positive 1, we subtract 1. Positive 2, we subtract 2. Okay. It's kind of counterintuitive to the charge, but maybe one way to look at it. If it's negative in charge, we add an electron. If it's positive, subtract. Okay. Then we put the brackets around the whole structure and we put the charge of that polyatomic ion on the outside of the species. Okay, let's try this one. The ammonium acetate. It's in your periodic table. All right, so we do the same like we've done before, nothing different. Okay, we got 1 nitrogen. Okay, let me change the color here. One nitrogen and 4 hydrogens. All right, so valence electrons, nitrogen is in group 5, so we bring 5. The hydrogen, each one has 4. Okay, now if we were to stop here and we add this number, we end up with 9. Okay, which is an odd number, which should be a flag to tell you, I got to do something. You're going to subtract or an add. Now, as stated up here, it's a positive cation, a positive ion. So we need to subtract from that number that we come up with. Okay. And so we end up with 8 valence electrons or 4 pair. Okay. Nitrogen is the central atom, so we do no different than we done before. We got nitrogen, and there's 4 hydrogens, so we can very quickly put in 4 hydrogens. Okay. Now keep track of your pairs. I got 4 pair around nitrogen. That took care of my pair. I got no more hydrogens to put on. Okay. Now, so I put my bracket, I put a bracket around the whole molecule and I put a plus. Okay. Now I can also do a general formula here. No different. My general formula would be AB4, which if we go to the shapes table, guess what that is? Tetrahedral bond angle 109.5. Okay. Okay, I'm back. The thing's still acting weird. All right. So no different than what we've done before. The only difference is it's with respect to the valence electrons. The only change is one. If it's positive ion, we subtract from our valence electrons. And then at the end, we end up putting a bracket to designate it as a polyatomic ion. And we can still do a general structure or geometry, if you will, because we use the general formula AB4, which we go to the shapes table, and that would tell us tetrahedral. Okay, so and that's what we did here. 1 nitrogen has 5 valence electrons, 4 hydrogens, 4, and then we subtract 1 because of the positive polyatomic ion charge. And we end up with 4 pair. Nitrogen is a central atom, and we come up with that. Notice the bracket. We put a bracket around there, not a parentheses, but a bracket, and then the charge in the very top right corner. So don't forget the bracket. Don't forget the charge. Now, with respect to polarity, you'll be asked the question, was this thing polar? Well, it's kind of a mute point. Anything ionic, anything with a charge is polar. Okay. But the overall is polar. The bonds themselves will be a little bit different story. Okay, we'll talk about that here in a bit. All right, well, let's do these examples. Understood. You don't know, you may not know what these compounds are, but I'm assuming you don't. But observe what you've been given. You have BrO3. Okay. It's a polyatomic anion. And so you have bromine is a central atom and oxygen, 3 oxygens bonded around it. Okay. So no different. We got 1 bromine, has 7 valence electrons. We have 3 oxygens, each one brings 6. So that gives us a total of 18 valence electrons. And then it's got a negative charge, so we need to add one more to it. So that gives us a total of 26 valence electrons or 13 pair. Bromine is the central one. Okay. And I think I can draw that. Let me do this. Okay. Bromine is the central atom. Okay. Then we got 3 oxygens around. I can do that, that, and that. And that took care of 3 pair, correct? So I got 10 pair left. Now, where you put them, totally up to you. Like I stated before, I started on the outside and worked my way in. So I'm going to put 10. 1, 2, 3, 4, 5, 6, 7, 8, 9. And now I can't put any more in the oxygen. So the only place I can put that is in the central bromine, because now everybody has 8 electrons around it. Okay. Now, then I can put my bracket, okay, with my negative charge on the outside, top right corner. And a general formula, if I need it, will be A, B, 3E, okay? Because I got three oxygens bonded around my central atom, which is bromine. And then I got one lone pair in the central atom, okay? Would it have a double bond? All right. Now, let me ask you this. Where would I put the double bond though, Spider? So if I take, because remember, I only have 13 pair to work with. So if I put, let's say I make a double bond right here. Do I make a double bond? Okay. What happens to bromine? Yeah, 2, 4, 6, 8, 10 around bromine. So that wouldn't work. You gotta keep in mind the octet at all times. Now there are some atoms that can do more than 8, but those are exceptions to the rule. That's beyond the scope of Chem 130. Let me tell you that right now. Yes, there are some. We're not going to talk about those, but always remember the octet rule for Chem 130. But there are exceptions, FYI, that some species can handle more than 8. Okay? All right. That's good question. So let's clear this up and let's see what do we got. There we go. That looks familiar, huh? Yeah. All right. So let's do the next one. SO4 -2. All right. You'll be quite familiar with this one. This is called sulfate. You probably eat it next time you look at the label of some of the things you eat. You're going to see a lot of sulfate in there. This is what you're eating. The structure, that is, it's a salt. All right, polyatomic salt. Huh? So sulfur brings in 6, okay? Oxygen, there are 4 oxygen. Each one brings in 6. That's a total of 24 valence electrons. And then we have a -2 charge, okay? So we can add a -2 to that. So that gives us a grand total of 32 valence electrons or 16 pair, all right? So now I can draw the structure. And so I know that sulfur is the central atom because I'm told that. And even if you're not told, 9 times out of 10, the first atom, the first symbol written is a central atom, okay, FYI. Exception of H2O, that's always written with hydrogen up front. And some acids that we're going to talk about. All right, so we got sulfur in the middle, and then we can quickly bond 4 oxygens around it. Okay, so that takes care of 4, right? So now we got 12 valence electrons to work with because we have 16 pair. Just took care of 4. And so now where I put them is, well, your choice is your choice, but you can't put them on sulfur anymore, all right? Because sulfur has 4 around it already. And so those 12 just simply go around the oxygen. So I go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and 12. So I got those 12 there that I just took care of. So now I got 0 pair left. I still have 16 pair. So I'm good to go. I can put my bracket now and a -2. And I can do a general formula of AB4, which we look up the shape. Guess what? Tetrahedral. All right, tetrahedral salt. Okay, and that is the structure. And then finally, cyanide. This is the structure for cyanide. It's got a negative. You all heard it, like sodium cyanide. This is very similar to HCN. The only difference is the hydrogen is missing. Okay, And so we got 4 valence electrons from carbon, 5 from a nitrogen, and then it's a negative charge, so we add 1 more, so we get a total of 10, okay? And so, or 5 pairs, so now it's just a matter of making double bonds, in fact, or triple bonds, and that's what happens, just like we did with HCN, and we ended up with this particular structure. Don't forget the brackets. Okay. All right. So basically, again, when it comes to the polyatomic ions, same procedure, adding up the valence electrons, except the difference is 2 differences. One, we either add or subtract, depending on what type of charge and the amount. And then we put a bracket around the final structure and with the charge on the top right corner. And we can also give it a geometry, just like we did the previous examples. The non-polyatomic, the regular compounds that we did earlier. Okay. Now this thing here, I just introduced that to you earlier. When I was talking about lone pairs and them occupying space, but they do have a model and they call it the valence shell electronic pair repulsion model, or the VSEPR. Basically, all that means is this: those electrons have negative charge, and as we know, opposite charges repel. And so what's going to happen is, depending on the charge and the electrons, they're going to repel each other, and they're going to put themselves in a position so they have optimized that repulsion forces. Okay. That's why I said in the tetrahedral shape, it was that particular shape, because those electrons on the bonds, they're repelling each other. And if we had magnets to show that, they would automatically be if I had a set of magnets that can really demonstrate how, because of the force, that would be the optimum configuration for them, where they have the maximum repulsion position from each other. And that's what all this does. Okay, so the shape of molecules is determined by the electrons. Okay, so I've already introduced you to this general equation where ABE, where A is a central atom, B is whatever's bonded to the central atom, and E are the lone pairs on the central atom. That's important. The lone pairs on the central atom. We don't care about the lone pairs on other atoms, only on the central atom. All right, we have the diatomic elements. Okay, this structure on the left, and then you got the space fill model to kind of represent what it looks like. This is chlorine. Okay, there's only 2 atoms, diatomic. All the diatomics, have no fear of isobarrier, have this structure, this geometry. And just by default, it's linear. Okay, and there really isn't a bond angle here, because there's no way to, a bond angle is reference to at least 2 bonded atoms to the central atom. So there's no bond angle here. All we can say that it is a linear species. All diatomic moieties are linear. Okay. Carbon dioxide, we did that example earlier, and that is also linear. Okay. That double bond kind of locks it in position, be linear in structure. We're going to learn that the carbon dioxide has what we call polar bonds, but this species carbon dioxide is really nonpolar. All right, another shape called trigonoplanar. Here's an example, and where you got a carbon double bonded to oxygen, and then you have a single bonded hydrogen. This example is a formaldehyde. This is the formula for formaldehyde, FYI. Cancer-causing chemical, used to be used to preserve. If you ever had a biology class and you were dissecting pigs or something else, they normally stored them in formaldehyde. They don't do that, I'm told, anymore, because it does cause cancer. Anyway, trigonoplanar. and 120 degrees bond angle between the, all the way around. The most common geometry, again, here's that model, kind of helps you kind of perceive it three-dimensionally. This one here is called methane. It's a hydrocarbon. We call it hydrocarbon because it's made up of nothing but carbon and hydrogen. Okay, carbon, hydrogen, and you're familiar with these hydrocarbons. A butane, if you have a lighter, and if you did some cookout, you probably use some propane. That's a hydrocarbon too, and it's made up of nothing but carbon and hydrogen. The bond angle here is 109.5. Generally, that's our reference bond angle. A lot of things have that particular bond angle. Okay. The ABE is called the bent configuration. This example here it's a nasty smelling gas, SO2. This is called sulfur dioxide. Okay. We would think that this bond angle again would be 120 degrees like the other one we did earlier because of this. But remember, these lone pairs on sulfur take up a lot of space, so that shrinks this angle a bit, much less to be 120 degrees. All right, so there's an example of an ABE configuration. We did ammonia. Ammonia is a trigonal pyramid, which, by the way, this one is polar, lone pair on the central atom, polar. Okay, you'll know more about this here in a bit. Here we go again. Ammonia, lone pair in the central atom, polar species. We also did this in the examples of the structure. Again, that bond angle is much less. Bond angle is less than 109.5. Again, because of the lone pair taking up more space. Okay, and you can see the model here, how that's kind of pushed down a little bit. And then water. Water is extremely polar species. Two lone pairs on the central atom. That bond angle really says less than 109, but it should really be much less than 109.5 because those four lone pair electrons take up a lot of space, squishing those hydrogens and to each other closer. Okay, so water. Now, summarize all this. You might want to given any covalent molecule or polyatomic ion, you should be able to draw the electron dot structure, and from the shapes table, determine the shape based on this general formula and the bond angle. Okay, and don't forget the shapes table. So you might try these, and if you can't get it, we'll bring it to class next time. We'll work it through. So pH3 is one of the species, and then ozone. Ozone, by the way, you're familiar with ozone. There's actually two. There's only one type of ozone. It's O3. That's its formula. But there's the ozone here around us. It's just not good for breathing reasons. Health hazard. We generate quite a bit of it. And then there's another ozone up in the upper atmosphere, which is very important. It protects us from the UV radiation of the sun, reacts with the UV radiation and actually regenerates itself. However, we as humans punched a hole in it because a lot of these hydrocarbons we were using before for propellants and so forth get up there and they start destroying the ozone, which causes more UV radiation to hit the earth. So if you notice, there are protection for sunblocker is pretty high value compared to back in the day when I was a kid. All right. Now, which brings us to a very important concept, okay, which is called bond polarity. And this only applies to covalent bonds. Those are those molecules that share electrons, okay? That share electrons. Has nothing to do with ionic. Ionic bonds don't share electrons. They have a full-fledged positive, a full-fledged negative charge, okay? Now, how does this work? Remember we talked about electronegativity. All the atoms have a En value, not to be confused with ionization energy. Ionization energy, to refresh your memory, was the amount of energy necessary to remove an electron from a neutral atom, okay? Electronegativity is the affinity for an atom to pull electrons onto itself in a bonded situation. So these guys are bonded to something, all right? When they're bonded to an atom of equal electronegativity, then that bond is equally shared, and it creates what is called a non-polar bond. What we mean by polar, I mean, can you think of an example other than chemistry where, other than the polar pop at Quick Trip, can you think something around you that you know that is polar? I can say, this is polar. Can anybody think of something that's polar? Yeah, well, I'll give it to you this way. You've been on it since the day you were born. Does that help? Yeah, the Earth, exactly. A magnet is polar. Your battery you're using, if you're using a battery and now is polar, the battery in your car is polar. You get a positive end and a negative end, okay? And so we're talking about something that has, in this case, maybe a positive end and a negative end. Okay, so it's polar, like the Earth. We got a North Pole and the South Pole, exactly. And that is crucial, and that's very important. The polar bonds are very important in chemistry, where without that, it would be very difficult to make a lot of the compounds that we make for medicinal purposes or whatever we're making as organic chemists. Okay. When we have a covalent bond, remember covalent bond is a shared bond. Okay. When there is unequal sharing, we have a polar bond. Now, I gave you a resource. Where do you go? On the website. And let me pull it up real quick. Okay. It's called molecular polarity. So you may want to use this as a guide to help you understand the concept of polarity. So if you pluck it, it has its own modules. To select the one called molecular polarity, and you can I'll select the 2-atom one. Okay. So in this case, I have 2 atoms, A and B. Okay. And I have a scale down here at the bottom. And right now, the scale in A is to the far left. They're both equal. So in this scenario, the electronegativity of A and B are equal. And we have what is called a non-polar bond. There is no tug of war in the sharing of those electrons, that electron in the middle between A and B. Now, when the electronegativity of one of the atoms gets increased, this is what happens. I'm gonna double it. I'm gonna go like this. All right. The red indicates what is now, with B having more a higher electronegativity, it is pulling the electrons onto itself much more than A is. The result is, remember, electrons have a negative charge. So there's more electron density around B, resulting into what we call a partial negative. is given by the lowercase delta symbol, which looks something like, let me draw a different color here. Lowercase delta, something like that. And we go either positive or delta negative. It's right there. You see that? And the color becomes red there. Okay. And it becomes more negative because the more electron density is being pulled onto a cell. Keep in mind, when the electronegativity is equal, no dipole. I start increasing the electronegativity of one of the moieties here, B, I create what's called a dipole. And we designate that by that arrow that you see being created there. That is called the dipole arrow, okay? The arrow is the negative, partial negative side, and that plus on the tail is the partial positive side. Not a full-fledged charge like the ionic compounds, but a partial part of a positive charge. The result is, let me clear it a little bit, is by creating this partial positive side, I can rotate this. I can put an electric field, and here's a plate. You remember how the electrons were found by putting a magnet or a J.J. Thomson's work using a battery or a magnet or a charge plate. It will cause the deflection of the electron because of the charge. Well, when we put a partial, that partial negative is going to be attracted to the positive plate, right? And that's why you get it to rotate like that, okay? Because the electron density now is being pulled toward the B. And let me take that off. Okay? And we create a dipole, and we have a dipole area. Okay, this is a polar bond. This is a non-polar bond because the electronegativity is the same. Okay, and to determine which direction, which A or B, which direction the partial negative goes to, depends on the electronegativity of the atom, which depends on this position on the periodic table relative to fluorine, okay? So, but this is a polar bond, and use this simulation to help you with the concept of polarity, polar bonds, and so forth, okay? Because of the electronegativity difference in a bond, it's going to result in one of those atoms pulling the electrons closer to itself, which results in a polar bond, which, depending on the conditions, results in a polar molecule, okay? With respect to nonpolar bonds, regardless of anything else, when you have nothing but nonpolar bonds, all nonpolar bonds, guess what? You have a nonpolar molecule. When you have polar bonds, most of the time you have polar molecules unless those polar bonds cancel out. And I'll explain that here in a bit. All right, so refresh your memory on the electronegativity you need to. It's just the affinity for an atom to pull electrons onto itself. So let me pull up this. Okay, so as I stated earlier, fluorine is the most electronegative. And so if I needed to compare, let's say I had a carbon-hydrogen bond, okay? And I needed to know who's more electronegative, carbon or nitrogen. Who would be more electronegative, carbon or nitrogen? And that would be true. Nitrogen. Why? Because it is closer to fluorine, so it has a higher electronegativity. Yes, all these elements have absolute values of electronegativity. Yes, if you want to memorize all of them, you go right ahead, that's fine. Or just remember, fluorine is the most electronegative, and whoever's closer, the trend goes from left to right, it goes up. From bottom to top, the electronegativity goes up. So using fluorine as my reference point, I can determine who's more electronegative. By the same token, oxygen is more electronegative than nitrogen. The fact that carbon is more, nitrogen is more electronegative to carbon, if they were bonded together, guess what? I would have a partial negative on nitrogen and a partial positive on carbon because nitrogen is pulling the electrons onto itself much more than carbon. Okay. Let me clear this and go back. All right. Now we know noble gases don't have electronegativity. Why? The octet is full. There's no place. It doesn't want any electrons. Their octet is full. Okay. And remember, that's the trend. Left to right increases, bottom to top increases. Okay. Now, nonpolar bonds. All of the diatomic molecules have nonpolar bonds. Why? Because they are bonded to the same element that has the same electronegativity. Therefore, they are sharing the electrons in that bond equally. Okay, there's no pole. The other example where you might think you have two different elements, and you would think you have a dipole, is carbon hydrogen. Carbon hydrogen, the electronegativity of carbon hydrogen, their values are relatively the same. Yes, I know hydrogen's in the far left in product table, and using that trend, you would think hydrogen is a lot more less electronegative than carbon, but that's not the case. They're actually pretty close to each other. So for Chem 130, the electronegativity of carbon and hydrogen is essentially the same. Hence, any carbon hydrogen is a nonpolar bond. Okay, any carbon hydrogen bond is a nonpolar bond. All diatomic molecules are nonpolar bonds, and therefore any molecules that contain nothing but carbon hydrogen are nonpolar. Okay, and will dissolve more in an oil solvent than they would in a water solvent, aqueous system, a polar solvent. Okay, so now we talked about polar bonds. So anything else, any two atoms that are different except for carbon hydrogen are you have essentially a polar bond. Okay, just remember that. Any two different, okay, let me restate that. Any bond that contains different atoms give you a polar bond, except carbon hydrogen. Okay, I'll repeat that again. Any bond that has two different atoms is a polar bond, except carbon hydrogen. And so these examples of carbon oxygen, hydrogen chloride, sulfur fluoride, silica nitrogen, all polar bonds. Okay, all polar bonds. You don't even have to think about the fact that they're different. They're polar bonds, except carbon hydrogen. Okay. Now we can indicate, now that we know that they're polar bonds because they're two different elements. Now the next thing is, well, where are the electrons? Where is the partial positive and a partial negative in that bond? And that is determined by the electronegativity and their relative position relative to fluorine. So if we look at carbon fluoride, we just stated fluoride is the most electronegative element there is. So without even having to go any further, fluoride in that carbon hydrogen bond will have the partial negative charge. And the carbon by default has a partial positive. and the arrow will go in the direction toward fluoride, in this case from left to right, okay? Left to right. If we look at an example of oxygen and hydrogen, again, we have a polar bond, two different elements. In which direction the polarity runs? Oxygen. Why? Because oxygen is a lot more polar than hydrogen. Therefore, oxygen would have the partial negative and hydrogen will have the partial positive. And the arrow, a dipole arrow here would be written from right to left because that's how the bond was written. If it was the other way, okay, here's something to keep in mind. If this was written with hydrogen first and oxygen here, well, no big deal. We're still going to oxygen because whether I write it from OH, HO, it doesn't change the polarity. It just changes which direction the arrow is, okay? And then finally, the bond between carbon and chloride, polar bond, okay? And it goes from left to right. Now, here's the thing about these arrows I want you to remember. We're not going to discuss these in detail, but if you want, you can look up the term vectors, VECTOR. That's fine. We're not going to go into detail. But vectors are nothing more than a measured, how can I state this? A moiety that has magnitude and direction, okay? And so that arrow, the way I wrote it, is going from left to right. The length of that arrow has a magnitude of value to some amount, okay? Whatever, it could be 10 units. Let's just arbitrarily say 10 units of something, okay? And it's going from left to right, maybe it's going east because it has direction. Now, the fact about these arrows is this. We can, if they go in opposite directions, they cancel each other out if they have the same magnitude. So if we have another arrow going in the opposite direction with the same magnitude of 10 units, for example, the net is equal to 0. Okay? We repeat that. The net is equal to 0. If they go in the same direction, then we multiply the magnitude. So what does this mean? Remember carbon dioxide? Carbon dioxide, we had that formula, right? We have a polar bond, two of them, left to right for carbon. Let me draw this a little better. It's kind of hard to see here. Okay, carbon dioxide. That's the structure we came up with. It has two polar bonds from carbon to oxygen because oxygen is more polar. It's going to the right direction. Then we have another one going in the left direction, okay? These two have the same magnitude. The net effect is a 0, which means that even though we have polar bonds, the molecule is non-polar because the polarity of the bonds canceled out. Okay. Okay. The question Skylar was asking is why is Ch considered nonpolar? Again, because the absolute value for the electronegativity of carbon and hydrogen is essentially the same. So their net, there's no net. They're basically nonpolar. Okay. We can look up the values of your absolute carbon, the absolute electronegativity of the different atoms. And then if you look at the difference between the two when they make a bond, there is a range that the difference, when it's a certain amount, it's nonpolar. When it's a certain amount, it's polar. So the difference in polarity and electronegativity between carbon and hydrogen, puts it in the nonpolar range.
Professor, I have a question.
Yes. Yes.
Could you give another example of a non-polar molecule, please?
Nonpolar.
Yes.
Okay. Well, anything like, for example, methane. Remember the structure. Hold on. Remember the structure for methane. Okay. Methane, when we write the structure for that, is tetrahedral. So it would look something like this. Okay. And so all four bonds are nonpolar. All four bonds are nonpolar. So we have a nonpolar molecule. Okay. Now, if we have a species where we have 4 fluorines, like this, we have polar bonds. We have 4 polar bonds. However, these 4 polar bonds cancel out. So we end up with a non-polar molecule. Okay? Non-polar molecule. So these are examples where you can have, like carbon dioxide, 2 polar bonds, but because they cancel each other out, all these cancel each other out because there is a dipole going from the carbon to each of the fluorides. And due to the geometry of this, and we can go into the mathematics, but we're not going to do that. Those 4 polar bonds geometrically cancel all each other out because they all have equal polarity. Okay. All right. Hopefully that would help. I tell you what, I need to get going here. Barbara, did that help you out with your question?
A little bit.
Okay. Well, send me an email and see if I'll send you some more. You're wanting to know more examples of what? Polar bonds and non-polar?
No, I understood about the difference between polar bonds and no polar bonds. My confusion comes with the molecular because on the video, they only show one example of a no polar molecular. So I'm confused to really to understand when we can figure out a no polar molecular, because I understand the difference about the bonds, but the molecular I don't.
You mean the molecule?
Yes.
Yeah. Again, well, you might mute yourself. When you look at the polar bonds, you said you understood the polar bonds. If the polar bonds cancel each other out, then the molecule is nonpolar. Okay. If they do not cancel each other out, then the molecule is polar. Does that make sense? So that's where the geometry, when you come up with the Lewis dot structure, you look at the 3-dimensional model, and then you look at the polar bonds. If they cancel each other out, then the whole molecule is nonpolar, just like carbon dioxide. But if they don't cancel out, and I'll have some more examples here in a few more slides, but we will continue with that on Tuesday. Okay. Maybe that helps you. It's when you talk about you don't understand the molecule, the molecular, you're talking about the molecule overall, correct?
Correct.
Right. So in general, if all the bonds are nonpolar, the molecule is nonpolar. Okay. Number 1. Number 2 point. If the bonds are polar and they do, okay. If the molecule has all polar bonds, generally they are a polar molecule, unless the polar bonds cancel out. Okay? Look at it that way. All right, well, let me stop it here. Think about that, Barbara, and see if that helps. Then
Thank you.
I will see if I can come up with some more examples for you, for everybody.